Hello everyone. In this lecture we'll continue with the chapter Gaseous State in Thermodynamics, and we'll learn what is the equipartition of energy, and we'll learn what is the total energy per molecule in various type of molecules like diatomic, polyatomic or monoatomic gases, and we'll solve some questions based on the concepts we have learned till now about the ideal gas. Okay, so let's begin with the first thing, that is the equipartition law of energy. Which says that it is nothing but the law states that for a dynamical system, in thermal equilibrium, the total energy of the system is equally divided amongst the various degrees of freedom. Basically, it says that the division of the total kinetic energy is uniform across the all degrees of freedom. So the share of each degree of freedom is kT by 2. Okay. So by using this, we can find the total kinetic energy or total energy for various type of gases. So first we will begin with for monoatomic gases. Which are basically consisting of only 3 degrees of freedom that are corresponding to translation only. So total energy per molecule is nothing but 3 times into the energy per degree of freedom, that is kT by 2. Therefore 3 by 2 kT. Similarly, the total energy per mole is nothing but 3 by 2 kT into Avogadro's number. And as you know, K into N naught is R, so 3 by 2 RT. So it is the total energy per mole of a monoatomic gas. Similarly, for diatomic gas, you can have the total energy per molecule is nothing but 5 is the degree of freedom into kT by 2. That gives us 5 by 2 kT. Similarly, total energy per mole is equals 5 by 2 RT. And as we know, for the triatomic gas, the degree of freedom is 6. So it will give us total energy per molecule equals 6 into kT by 2, or we can directly write it 3 kT, and total energy per mole is 3 RT. Okay. So now let's do some questions based on the ideas we have learned till now about the ideal gases and the various other concepts. Okay. So the first question is very simple. It says that calculate CRMS of argon gas at room temperature, which is 25 degrees Celsius. And the second question is, at what temperature will CRMS be half of this value? What is the value of the CRMS right now, and at what temperature will the CRMS become half of the present value? Okay, so we know that CRMS is nothing but root 3 RT by m naught. The important thing over here is this is the molecular mass, or we can say the molar mass in kgs. Okay, and similarly R is also in SI units, and temperature is in Kelvin. So most important thing is the units of the values we are dealing with. So CRMS equals 3 into value of R in SI units, that is 8.3. R is equals to 8.3 joules per mole per Kelvin. Okay, so we substitute R value, that is 8.3, and the value of temperature is in kelvins, that is 273 plus 25 degrees Celsius, as you know it. So it would give us the temperature in Kelvin. Mass is basically molar mass. Molar mass of argon is 40 grams. That would be equals to 0.04 kg in the SI units. So we can substitute it. If we calculate it, it will come out to be 3 into 8.3 into 298 divided by 4 into 100 square root, which would come equal to 430.7 meter per second. Okay, so this is the root mean square velocity of the molecules. That is, it is the roughly the speed at which the molecules are moving. It is a very high velocity, as you can see it, 430 meters per second, and that is approximately also equal to the speed of sound as well. That is around 340. So it is a bit greater than the speed of sound, because you can think that air is also a combination of various types of gases, and at room temperature this is approximately, the whole air is a combination of various types of gases, so the speed would be something around this only. Okay, now the second question was, at what temperature the CRMS would become half of this value. So we are dealing CRMS 2 would be CRMS 1 upon 2. This is what we are interested in. Okay, so we can say that CRMS 2 upon CRMS 1 is basically half, which is equals to root 3R T2 upon M upon 3R T1 upon M. We can see 3R cancels out, M and M cancels out. So half equals T2 upon T1 root. We can square the terms, so we will get 1 by 4 equals T2 upon T1. So T2 is nothing but T1 upon 4, and T1, as you know, is 273 plus 25 upon 4, that is 298 upon 4. That would give us 77 Kelvin. Correct? So if, sorry, my mistake, it is 74.5 Kelvin, which is nothing but T2 equals minus 198.5 degree Celsius. So at such a low temperature, the CRMS would be half of the original value. So this was a simple question just based on the formula based of the CRMS velocity, but the important thing here was you have to convert each and everything into the SI unit to find the answer in the meter per second. Excuse me. Yeah. Let's do one more question. It says that calculate the pressure of hydrogen in a cylinder of capacity 10 liter, given that total kinetic energy of translation is 7.5 into 10 raised to power 3 joules, and the second question is, what is total kinetic energy of the molecules? Okay, so this is given to us. So first of all, you must be knowing that H2 is a diatomic molecule, correct? So it has 5 degrees of freedom. Now you are given that the hydrogen is stored in a 10 liter vessel and the kinetic energy of translation is given to be 7.5 into 10 raised to power 3 joules. Okay, so if we remember from our previous formula that we derived for a gas, the total kinetic energy or the average kinetic energy for a molecule in terms of translation energy. So the total energy that is kinetic basically of translation per molecule was 3/2 kT. So kinetic energy, total kinetic energy of translation in n moles would be 3/2 K into n naught into n into T. As you know, K into n naught is R, so 3/2 nRT. Now as you know that we are dealing with the ideal gases, so PV is equal to nRT holds. The ideal gas equation holds, so we can replace nRT by PV. So we can say that total kinetic energy of translation is equal to 3/2 into PV. Now we know that the pressure is basically 1 atm. Okay, and 1 atm is atmospheric pressure, that is equals to 10 raised to power 5 Newton per meter square. That is its value in the SI units. So the total kinetic energy of diatomic gas would be nothing but 5/2 PV, because this was corresponding to 3 degrees of freedom. Because translation is possible in only 3 directions, that's why it was corresponding to 3 degrees of freedom. And as we are dealing with the H2 molecules which have 5 degrees of freedom, so the total kinetic energy of the diatomic gas will be 5/2 into PV. So this could be calculated as 5/2 into pressure, that is 10 raised to power 5 Newton per meter square, into volume, that would also be required to be in SI units, that is meter cube. This is required in meter cubes. This is required in Newton per meter square. So the volume given us is 10 liters. So 10 into 10 raised to power minus 3. Correct? So this would give us 10 square. So 5000 upon, sorry, the one thing we did wrong was basically, we didn't calculate the pressure over here. One ATM is given to with this. We have to calculate what is the pressure at present. We are given that the total kinetic energy of translation is given to be 7.5 into 10 raised to power 3 joules. So we have the information that 3 by 2 PV is basically 7.5 into 10 raised to power 3 joules. Either we can use this equation directly to calculate 5 by 2 PV, because you can calculate PV, that would be equals to 2 into 7.5 into 10 raised to power 3 upon 3. So this would be 2.5. So it would give us 5 into 10 raised to power 3 joules. And we can directly use it to calculate the total kinetic energy, which would be equals to 5 by 2 into PV, that is 2.5 into 5 into 10 ki power 3, that is 12.5 into 10 raised power 3 joules. Okay. So in this basic question, we utilize the fact that the degrees of freedom known to us and the formula for the total kinetic energy of translation that we know, that is equals to 3 by 2 nRT or 3 by 2 PV. And that is corresponding to 3 degrees of freedom. And similarly, for a diatomic gas, there are total 5 degrees of freedom. So we have to multiply it by 5 by 2. Okay. Now let's try and do some more questions based on the things we have learned till now. So the third question is that find number of hydrogen molecules in 1 centimeter cube if the pressure is 200 millimeter of Hg and CRMS velocity is equals to 2400 meter per second in these conditions. So basically what you are given is a hydrogen gas under the condition such that it has a CRMS velocity 2400 meters per second and the pressure is 200 millimeters of Hg. Okay. So first of all, you must be able to convert the pressure in the SI units, because you have the velocity in the SI units, and this is given in terms of mm of Hg. So one thing I want to tell you is 760 mm of Hg is basically equals to 1 atmospheric pressure, that is nothing but 10 raised to power 5 Newton per meter square. So by using this conversion, you can basically convert this 200 mm of Hg. So you can find 1 mm of Hg is nothing but 10 raised to power 5 upon 760 Newton per meter square. Similarly, 200 mm of Hg is equals to 10 raised to power 5 upon 760 into 220 Newton per meter square. So this is the pressure in terms of SI units. Okay. Now you have to basically find is the number of hydrogen molecules given the pressure is this and the RMS velocity is given by that. Okay. So now we are using this fact. So the volume is basically given to us 1 cm cube. So we would have to represent this also in terms of the SI units. So this would be, as 1 centimeter is basically 10 raised to power minus 2, so it would be 10 raised to power minus 6 meter cube. And as we know that the mass of a single molecule can be known as m naught equals to total mass upon Avogadro's number, where Avogadro's number is 6.023 into 10 raised to power 23. Now if we substitute in the direct formula we have learned earlier, that pressure equals 1 by 3 into rho into C square RMS, or we can say 1 by 3 into m naught into n upon V into C square RMS. Now if we substitute the values, we can get the value for n, because we have the value for pressure, we have the value for volume, we have the value for m naught because we know that it is a hydrogen gas molecule. Okay, and similarly we have the value for CRMS. So we can calculate n is equal to 3 into PV upon m naught into C square RMS. Okay, so now we have all the values required to calculate the answer. So it would be 3 into pressure, that is directly we put from here 10 raised to power 5 into 220 upon 760. Okay, now we require volume, that is 10 raised to power minus 6. Then we require m naught. Okay, so m naught is hydrogen molecule weight. This is nothing but m naught is one molecule's weight, that is, first we consider the whole molar weight of hydrogen, that is 2 grams upon Avogadro's number n naught. That would give us the molecular weight of one molecule. So first we have to deal with the SI units, so it would be 2 into 10 raised to power minus 3 upon Avogadro's number. Okay, so we will substitute 2 into 10 raised to power minus 3 over here, and Avogadro's number will go up 6.023 into 10 raised to power 23 into C square RMS, that is 2400 into 2400. Okay, so we can see what value this gives. This would be basically 10 raised to power 5, this is 10 raised to power minus 1, 10 raised to power 22, 2 zeros from here, 2 zeros from 10 raised to power 18. Okay, so if we evaluate this would be basically 4.17 into 10 raised to power 18 molecules. So these number of molecules are present in this volume. So in this question we use the formula for pressure, that was, it is dependent upon the density of the gas into C square RMS. Now the pressure was given in terms of mm of Hg. Then we learned the concept that 716 mm of Hg is equals to 1 atmospheric pressure. So we converted this into SI units. The volume given to us was 1 cm cube. So we tried to find the total mass of the gas present. That was given to us. Okay, so using that we found the density and we could solve the total number of molecules present. Okay. So let us do one more question. That would be the last question for this lecture. Okay. So let's suppose the question is, a vessel A with a capacity 3 liters capacity V1 equals 3 liters contains gas at pressure P1 equals 2 atm, and vessel B with capacity with volume V2 equals 4 liters contains same gas at P2 equals 1 atm. The temperature is 0 degree Celsius in A and 27 degrees Celsius in B. Now, if the vessels are connected to each other, now vessels are connected by a tube, what will be the pressure in the vessels? Okay, I hope the scenario is clear to you. There was first a vessel A, another vessel B. It had a volume 3 liters, gas at a pressure of 2 atm at 0 degrees Celsius. Here the capacity was 4 liters, gas was at 1 atm and the temperature was 27 degrees Celsius. Now there was let's suppose a tube connected between them, and now they are connected to each other. So what would be the final pressure in both of them? Okay, so one thing is for sure, let's convert them into first kelvins. So this would be 273 kelvins and this would be 300 kelvins. Okay, so one thing is for sure, that the total energy in the starting and total energy in the end would be same, correct? Because there would be no loss of energy, because we are connecting them by a tube. So whatever the molecules had in store in the right hand side and the left side, when they mix, they also have the same energy. Okay, so let's suppose there were N1 moles in the A container, N2 moles in the second container. Okay, so we are saying that initial total energy equals final total energy. Okay, so initially we don't know first of all which type of gas it is. Either it could be monoatomic gas, or could it be diatomic gas, or it could be triatomic gas. So we are assuming the degree of freedom is equal to X. Okay, so for both the containers, the degree of freedom would remain the same, because we are dealing with the same gas only. So we can say that X by 2 into N1 RT1 would be the initial energy of gas in A, because N1 is the moles of gas present, and RT1 would be the RT1 by 2 would be the energy stored in the molecules of that gas, and X is the degree of freedom, so it is multiplied with X. Similarly, X by 2 into N2 RT2 would be the energy stored in the initial energy of gas in B when they are mixed, basically. So both would be having the same temperature, and the degree of freedom would be same, and the moles would be basically added up. So this would be the scenario, because the total number of moles, the whole of the gas had been mixed up, and both the temperatures would be same in the containers. That's when the total equilibrium would have been attained, correct? So we have to basically find this value of temperature. Okay, so we have to deal with this. The temperature could be found out by a formula which says that temperature is equal to N1 T1 plus N2 T2 upon N1 plus N2. This you can directly infer as well, because there are N1 molecules having the energy T1, N2 molecules having the energy T2, so, and the total number are N1 plus N2, that would be equally distributed on all of them. So the total average temperature would be N1 into T1 plus N2 into T2 upon N1 plus N2. So the temperature could be calculated. Correct? The temperature would be N1 would be nothing but pressure into volume upon NR. P1 upon V1 upon R into T1 plus N2 into T2. So similarly we can calculate basically the moles for both of the containers. So let's try and calculate with them for separately. So N1 would be P1 V1 upon R T1. Pressure was 2 atm. The volume was 3 liters upon R, that would be 0.0821 into temperature, that was 273 Kelvin. So N1 is this, N2 would be P2 V2 upon RT2. So basically pressure was 1 atm into volume was 4 liters upon R is 0.0821 into 300. This would give us N2. If we substitute, we'll get the temperature here because we have all the required terms. T1 also we know, N1 also know, N2 also, and T2 also. So this gives us temperature equals to 283.2 kelvins. So this would be the equilibrium temperature. Okay. So using this equilibrium temperature, we can find the pressure as well. So the pressure would be given by, at that scenario, what we would have is, when both the gases have mixed, there would be a condition PV is equal to nRT, where the pressure would be, what we have to find, volume available will be V1 plus V2, both the containers, moles would be N1 plus N2, R into the final temperature, that is 283.2. So that would give us the pressure required. Pressure would be N1 plus N2 into 0.0821 into 283.2 upon volume available, that would be 3 plus 4. N1 and N2 have been calculated over here. This and this, we have to add them up. So this would give us a final pressure that is equals to 1.43 atm. So basically this question wasn't anything different. You have to just analyze that the final and the initial energy have remained same. That would give us an equation between N1, basically the equation between the two states before mixing and after mixing, and the temperature could be related by this relation, and so rest is basically calculation only. In the next lecture we will learn what are the gas laws, various gas laws like Boyle's law, Charles law, Avogadro's law, etc. And we will learn more concepts and we'll try to do some questions based on them. Thank you.